Hi, this is John Carzola, your instructor, and I wanted to talk about a few things from Chapter 1. Hopefully you're reading that by now, but you may have noticed Chapter 1 talks about there's a lot of things in Chapter 1, and it just kind of gives you an overview of a lot of concepts that you're going to study more in detail later on in the book. So one of the big concepts is, where are we in the universe? And this picture from the book shows Earth right there in the middle, or in the front, sort of. And then we know, Earth is part of a solar system. The solar system is in a galaxy. The galaxy is part of a group of galaxies. That group of galaxies is part of a big cluster of galaxies. And that cluster is part of billions of other clusters of galaxies that are scattered somewhat uniformly throughout the universe. So that's kind of an overview of the picture of where we are in the universe. In the chapter, it goes through a bunch of different definitions of things. So these are things that we're going to study in more detail later on. So, what is a star? Basically, a star is a ball of gas. If you ever watched the Disney movie, I forgot what the name of it is. Anyway, Pumbaa Timon says, "What is that? What do you think those things are up in the sky?" And Pumbaa says something like, "Oh, I think they're just big burning balls of gas." And Timon was like, "Oh, that's crazy." And he gave some other complicated answer, but he was right. They're big burning balls of gas out in space, and we'll talk about these and kind of learn how we know what we know about them, and how we know what's inside of them, how are they formed, all these good things. Planets are things that orbit stars, and there's kind of a more precise definition of planets than what you see here. But it's something that is round and orbits a star, and it's big enough that it's kind of cleared its neighborhood of debris. There's no other large objects like it in its vicinity, so that's a planet. A moon is something that orbits a planet, often called a satellite. An asteroid is something that orbits a star and is kind of the orbits can be fairly random. They're generally not spherical. They're more just like blobs, leftover blobs from the early formation of the solar system. Comets are sort of similar to asteroids. They are more icy and dirty. Asteroids are dirty too, but comets have a lot of ice in them. And when they orbit the sun, if they get close enough, that ice vaporizes, and you're left with a trail of debris behind the comet as it goes around the sun. And it's that trail of debris that when we pass through it, if there's a trail of debris left behind in the Earth's orbit, when we pass through that trail of debris, we see a meteor shower. All these little pieces of material that are left behind by the comet as it passes through stay out there orbiting the sun, and the Earth passes through that occasionally, and that's where many meteor showers come from. Is passing through that debris, and then that debris hitting our atmosphere and burning up. And then the solar system we talked a little bit about, just our collection of planets and our sun and asteroids and comets and so on. A nebula is a cloud of gas out in space, big cloud of gas where possibly many stars are forming in the process of forming. So if you imagine how big one star is, these are huge clouds of gas where many stars could be forming. And so there's one star right there, and there could be a solar system around that star. And so think about the size of our solar system. That's just one right there, that one star right there. There's another one. And so this is just an enormous amount of space right here. But yet it's a very tiny part of our galaxy. This is a nebula that's in our galaxy, not in some other galaxy. This is still in our galaxy. Our galaxy is a kind of a disk of stars and gas and dust. It has different components that we'll talk about. You can kind of see it has a bulge in the center. It has certainly a disk of material around here. And there's also something called a halo of stars kind of around it. And there's some interesting things about galaxies and how they're formed, and how they help stars form, how they help recycle material from dying stars into new stars. And we'll talk about that in later chapters. The universe then is everything. What is the universe? Well, it's everything. It's all the stuff, all the galaxies, everything between the galaxies, inside the galaxies, and all that good stuff. So when we look at things, we see the light that they give off. So when we look at the moon, we see the light that is reflected off the moon from the sun. It comes to our eyes. It takes about 1 second for light to travel from the moon to our eyes. And so really what we're seeing is the moon 1 second ago. because light took 1 second to travel from the moon. When we look at the sun, which you shouldn't do with your naked eye, but it takes light about 8 minutes to go from the sun to your eyes. So you're actually seeing the sun as it looked 8 minutes ago. If the sun were to suddenly turn off, you wouldn't know it for 8 minutes, and then it would turn off. But it would have already turned off. It's just that it takes 8 minutes for that sort of signal, that occurrence, that event, to reach us. A star Sirius is about 8 light years away. It takes light about 8 years to get here from Sirius. So we'll talk about this distance called the light year in a minute, and we'll think about how big that is. But this when you hear the word light year, that's not a time, it's a distance. It's the distance light travels in 1 year. The Andromeda Galaxy is it's a big galaxy like our Milky Way galaxy. It's in our local group of galaxies. It's about 2.5 million light years away. And so it takes light 2.5 million years to get to our eyes. So when we look at that galaxy, we're actually seeing it as it looked 2.5 million years ago. Not right now, but as it looked 2.5 million years ago. So it certainly looks different now than it did then. But we won't know that. We won't know how it looks right now for another 2.5 million years. So the light year. The light year, again, is the distance light travels in 1 year. It's about 10 trillion kilometers, or about 6 trillion miles. That's a lot. Just write that number out. 6 trillion. That's 6 with 12 zeros after it. That's a big distance. Here's that idea again of this thing called look back time. And here's a little galaxy that's 7 billion light years away. It takes light 7 billion years to reach us from that galaxy. And from what we can tell, the measurements that we've made so far, the universe is about 14 billion years old. And so you can imagine that if you look at galaxies further and further away, it takes light more and more time to get to us. But if the universe is only 14 billion years old, the longest that light can be traveling is 14 billion years. So really the furthest we can see is a distance of 14 billion light years away. That doesn't mean that there's nothing beyond that distance. That doesn't mean that there's nothing 20 billion light years away from us. There could very well be stuff 20 billion light years away from us. We just can't see it yet because light hasn't had 20 billion years of time to travel. The universe is only 14 billion years old. So those are some general ideas of the solar system, the universe, galaxies, and so on. Let's think more about the size of things. How big is the solar system? And the solar system's big, so what we want to do is we want to create a model where we kind of divide the sizes by some big number to kind of make them all smaller numbers that are more manageable. So if we take every distance in the solar system, the size of a planet, the size of the sun, the distance between the sun and a planet, take all those distances and divide by 10 billion. That'll make all the distances smaller. And so if we do that, the size of the sun is about 14 centimeters, about the size of a grapefruit. That's how big the sun would be if we took its actual size and divided by 10 billion. Earth, then, is the size of a ballpoint pen, a little tiny ball on the tip of a pen. That's about how big the Earth would be if we divided its size by 10 billion. And then its distance from the sun is only going to be about 15 meters. So imagine a grapefruit and a tiny, tiny little ballpoint of a ballpoint pen, 15 meters apart. There's a lot of space in between that's empty. And that's the distance. It's sort of the relative sizes and distances between the Earth and the sun. Here's a figure from your book, and it shows, in the top part, it shows the different planets with their correct relative sizes and the sun. So Jupiter's the biggest planet, and the sun is huge compared to Jupiter. But Earth, we think Earth is fairly big, but it's really not. It's actually pretty small. Look how small it is compared to Jupiter. Look how small it is compared to the sun. It's tiny. This is a sunspot. This is a place where it's a little cooler, and we'll talk about sunspots and what's going on here, but there can be some sort of intense activity coming from these sunspots, solar flares and stuff. But the sun the moon, or the Earth, can be smaller than these sunspots. There could be small sunspots, big sunspots, but this is like a storm on the surface of the sun, a little storm in a sense. The Earth is smaller than a storm on the sun. It's kind of crazy. Anyway, so Pluto over here, which technically we don't consider a planet anymore, we call it a dwarf planet. It's tiny. Eris is about the same size as Pluto. And look at how small they are compared to the Sun, compared to the Earth. Right? The Moon isn't on here, Mercury's on here. Mercury's bigger than Pluto. And then, so that gives you a sense of the sizes of the planets and the Sun. The distances, if you go to Washington, D.C. and you go to the mall, the Sun is mounted on a little stand near the National Air and Space Museum. And 15 meters away from it would be the Earth. And it would be a little ballpoint of a ballpoint pen. And then, so there's Mercury, Venus, Earth, and Mars all clustered within about 20 or so meters from that one spot. But look at how much distance then you have to cover to get to Jupiter on this scale. Again, we're dividing everything by 10 billion. Jupiter is really far away compared to the four what we call terrestrial planets. And then you almost have to double that distance to get to Saturn. And then you almost have to double that distance from Saturn to the Sun to get to Uranus. I mean, it's incredible how much empty space there is in the solar system. There's 4 planets kind of clustered really close, and then 4 planets that are scattered way out there. Huge distances between them. And then there's tiny little Pluto way out here. And way out here, you're getting into the realm of all the other objects, the comets and stuff like that. So Pluto is an odd object. It's not the smallest, or it's not the biggest of those types of what we call Kuiper belt objects. And so there are things bigger than it, and so we don't really consider it an official planet anymore. And so this gives you a sense of the sizes of planets and the distances between them. So what about stars? On this scale of 1 to 10 billion, how far away is the nearest star? So the nearest star is called Alpha Centauri. It's about 4 light years away or so. So how far do you think that would be? If it's about 15 meters from the Sun to the Earth on this scale, how far do you think the nearest star is? Take a second to think about that. If you want to pause the video, take a guess. One of those answers, is it a mile away? A mile is pretty big compared to 15 meters. Is it 10 miles away, 100 miles away? Is it 2,500 miles away? That's pretty big. So take a second, think about that. Okay. It's about 2,500 miles away. So think about the fact that, think about the Sun being in Washington, D.C., with about the size of a grapefruit. The Earth is about 15 meters away from it. The nearest star in our galaxy, closest star to us, is all the way across the United States. Another grapefruit. So there's a grapefruit here, there's a grapefruit here, and there's nothing in between. Absolutely nothing in between. Maybe some dust, but certainly no stars or planets or large, really large objects. And it's amazing how much empty space there is between the stars. So how big is the universe overall, the whole universe? Well, the Milky Way has about 100 billion stars in it, roughly. And most galaxies, they're similar. There's smaller ones, there's bigger ones. So we always say that like the average galaxy has 100 billion stars. And by roughly counting galaxies through various measurements, we find that there's about 100 billion galaxies in the universe. And so 100 billion galaxies times 100 billion stars, that's 100 billion, whatever the number that is. I don't know what the number that is. But written in exponential notation, it's 10 to the 22nd power. That's 10 followed by 22 zeros, or 1 followed by 22 zeros. That's about the same as the number of grains of sand of all the dry beaches on the Earth. Think about all the beaches on the Earth and all the grains of sand on those beaches. That's about the number of stars we have in the universe. It's incredible. So how did we come to be, kind of in general? Where did we come from? The idea, and we'll talk again more in detail about that, is that there was an event called the Big Bang that created mainly hydrogen and helium. And over time, that stuff cooled and formed atoms and molecules, and dust. And that dust ultimately formed objects that kind of swirled around. There were early galaxies. Within those early galaxies, stars started to form. And the stars stayed in the galaxy because it was all kind of bound together by gravity. And as stars were forming, here's a sort of an image of a star forming from some cloud of gas within that galaxy. The star forms, it lives its life, and eventually dies, and maybe it explodes or something. When it dies and explodes, it gives off all that material that it created while it was living. And we'll talk about all these things that are going on while a star is living. But it then disperses that material back out into space, and the galaxy kind of acts as like a recycler. It lets that material spread around and get collected into new clouds of gas and dust, forming new stars out of the material of the old stars. And so this process goes on and on and on, and ultimately, we could have planets forming around some of these stars, and possibly a planet Earth, and possibly life could form on that planet Earth. And so, all the elements that we see on the planet, the different metals, the different everything besides hydrogen and helium, were formed in stars, during the lives of stars. Stars, the earliest stars formed with pure hydrogen and helium, and maybe a trace amount of some other things. But they created the heavier elements, we call them, carbon, oxygen, nitrogen, all that good stuff that we need to live. And the stars died and dispersed that material out into space, creating more stars that ultimately then use that material to make planets, and the planets then have that material in them, and so do we. So we are the stuff of stars, ultimately. But what about the time? What about time? We talked about the age of the universe being 14 billion years, roughly. How does that compare to our lifetime? Let's say we live, 80, 90 years, whatever. Or if you're say you're 20 years old or so, how does that compare to 14 billion years? Well, what I like about this book is that it does this nice little sort of compression of the age of the universe into a single calendar year. And so you imagine that the universe was created on January 1st of some year, whatever year you want to talk about. Well, what happened throughout the year? Not a lot. There wasn't a lot of stuff that happened. It wasn't until, if you go all the way into December 31st, 9 p.m., the earliest hominids evolved. If you think about evolution, the earliest things that look like humans evolved. That's 9 p.m. That's 3 hours before midnight, 3 hours before right now. So right now would be midnight on December 31st. The Big Bang was January 1st, a year earlier. So 3 hours ago, the earliest hominids evolved. 2 minutes ago, modern humans evolved. 25 seconds ago, we started doing like farming and stuff like that. It was a long time ago in real time. 11 seconds ago, the pyramids were built. 1 second ago, Galileo and Kepler and so on showed that the Earth orbits the sun. So like 1 second is like 400 or 500 years on this scale. And that's incredible. So how long ago were you born? That was like a blink of an eye ago you were born. So I think hopefully it gives you a sense of how big of a time 14 billion years is. A blink of an eye is your lifetime on that scale. And then what about moving through space? What about movements? We'll talk more about these. So the Earth is rotating on its axis. That makes different points on the surface of the Earth move at different speeds relative to the center of the Earth, the axis of the Earth. So if you're on the equator, you're zipping around at a speed of about 1,600 kilometers per hour. Right? So the Earth is rotating on its axis. The Earth also goes around the sun. The Earth orbits the sun, and we call that the ecliptic plane, that sort of imaginary plane on which the Earth orbits the sun, revolves around the sun. The Earth is about what we call an astronomical unit away. It's about 150 million kilometers away from the sun. On that 1 to 10 billion scale, that was that 15 meters. So 150 million kilometers divided by 10 billion is 15 meters. So the Earth goes around the sun, and it travels at a speed of about 107,000 kilometers per hour. That's pretty fast. It's traveling around here. 107,000 kilometers per hour traveling around the sun. It has to travel a pretty big distance. It does that in 1 year. And then the sun and the solar system travel around the center of the galaxy. We're about 27,000 light years away from the center of the galaxy. Our orbit around the center of the galaxy is about 230 million years to go around there, 230 million light years. And or 230 million years to go around, not light years, sorry. And the stars around us are moving kind of randomly. they don't necessarily all move in the same direction. They move fairly randomly, but that grouping of stars moves kind of around in the same sense, this way around, this kind of in a clockwise sense as seen from this view. And so these stars moving kind of randomly are moving at about 70,000 kilometers per hour. Remember, the Earth is going around the Sun around 107,000 kilometers per hour. But the grouping of stars that go around the galaxy are moving at about 800,000 kilometers per hour. And think about how fast we're moving. We're moving around the Sun at about 107,000 kilometers per hour, but the Sun is moving around the center of the galaxy at about 800,000 kilometers per hour. It doesn't feel like we're moving that fast, does it? The reason why it doesn't feel like we're moving that fast is because, we'll talk about this in a later chapter, but we really don't feel speed. What you feel is accelerations. You don't really feel speed. If you're in your car driving down a nice smooth road going pretty fast, you don't really feel that speed unless you hit a bump or unless you hit your brakes or you press on your gas pedal. You feel those changes in your speed. You don't necessarily feel your speed very easily. So then when we look at galaxies, another thing we'll talk about in more detail later, we notice that as we look at the speeds of different stars around the galaxy, it doesn't quite behave the way we think it would behave by just thinking about gravity and what we know about forces and gravity and accelerations and stuff, and we'll talk about this later. So this hints to the existence of some other material in the galaxy that we don't have a good handle on. We don't really know what it is yet. So we give it a name, we call it dark matter. And it's something that we know must exist because the stars that we can see are not moving in the way that we think they should be moving. There must be something else there. So this is something we'll talk about later. This is different from dark energy that you may have heard about. We'll talk about dark energy later. And then so how do galaxies then move within the universe? Galaxies in general, the further out you look, the further away you look, we discover, Edwin Hubble discovered that these galaxies are moving away from us. So he looked at galaxies farther away, outside of our local group, and they're all moving away from us. Galaxies closer are moving kind of in random directions, but galaxies farther away are all moving away from us, which is kind of interesting. And the further away a galaxy is, the faster it's moving. So we conclude that we're living in an expanding universe. What is that? How do we kind of model that? If we look at this interactive figure from our book, this is in the study area on Mastering Astronomy. The analogy is this raisin cake. If we imagine that we're at this, we call this the local raisin. This is like our local group of galaxies, and we're in here. We look at a galaxy that's about, well, we'll call it 1 centimeter away. Okay, this is like at one moment in time, we see this configuration of galaxies. There's another galaxy cluster about 2 centimeters away, another one about 3 centimeters away. So 3 centimeters in total from our local raisin to that distant galaxy. There's 1 centimeter between each cluster of galaxies, 1, 2, and 3. So what we can do is we can let time go on and let time go here, and we'll see what happens. This is an expanding raisin cake. The cake is expanding. The individual raisins are not. Those individual raisins are our little clusters of galaxies. So let's see what happens when we play this. The cake expands, and the distances between adjacent clusters gets bigger and bigger and bigger. And now let's pause it right there. Now there's 2 centimeters between each galaxy. But notice that the further away you look, the faster these galaxies must be moving, because if you notice how much time went by, 30 minutes. 30 minutes of time has gone by. All right. How far did this galaxy travel? It was 1 centimeter away. Now it's 2 centimeters away. So it traveled 1 centimeter in 30 minutes. 1 centimeter in 30 minutes is how fast this galaxy traveled. 1 centimeter per 30 minutes, we can call it. How about this galaxy that was further away to begin with? This galaxy was 2 centimeters away total. Now it's 4 centimeters away. So it has traveled 2 centimeters. This galaxy has traveled 2 centimeters in 30 minutes. So its speed is 2 centimeters per 30 minutes. So it's traveling faster away from us than this galaxy was. What about this galaxy? It used to be 3 centimeters away. Now it's 2, 4, 6 centimeters away. So it's traveled a total of another 3 centimeters in this 30 minutes. So it traveled at a speed of 3 centimeters per 30 minutes. That's even faster than galaxy cluster 2 traveled. So you see in this model of this raisin cake, where the cake is expanding, the raisins are not, but the cake is expanding, and those raisins are kind of embedded in that expanding cake. We see that the further away we look, the faster things are traveling away from us. This is analogous to the universe. The universe carries with it the galaxies, clusters really. Again, the galaxies themselves are moving kind of randomly within their own neighborhood, but those neighborhoods, those small clusters, are moving away from each other because they're being carried by the fabric of space and time that's expanding. So hopefully this helps understanding some of the material. All these things that we talked about in this chapter are going to be discussed again in more detail in later chapters. So feel free to email me with questions if you have any, jcarzoli@oakton.edu. Have a good night.